me a question. Sorry. Let me check that. I see your question, Anthony. You could be wrong, but at the remove at head, wouldn't you want to set tail before you return false? Yes, if there's a problem. But let me look at that right quick. I don't know. So let's go to the remove at head. And if head is equal to null, return false. No, I don't need to set tail equal to false. The assumption here is that if head is ever null, tail is also. So in all my other methods, I have to make sure that that is true. An empty list has a head and a tail equal to null. So you'll notice at the bottom, if I removed the head, and if head is equal to null, I set tail equal to null. So I definitely do that. And notice that when I do the remove at, if the head node is removed, it will automatically be set to, it will automatically be set to null because I call the remove at head to ensure that. So I've made sure that my remove at and my remove at head both deal with needing to set the tail reference to null or to updating it to temp. I don't know why this did the brackets like this. I don't like that, so I'm throwing them away. Okay. If there were brackets, I'd want them to be up here anyway. Okay, so that's a good question, damn good question. And so here with my driver, I was just going to add the head value. And get tail value just to look at them. It's not a huge deal, but it can help you see the beginning and the head, and so what we could see is I enter a 7 at position 0, not 09, but 0, and there it says there's a 7, the head is 7 and the tail is 7. So let's insert a number 5 at position 1, and now we've got 7 and 5. The head is 7 and the tail is 5. Let's insert position or number 9 at position 0, and now the head is 9 and the tail is 5. And it's keeping these maintained, which is what I really want. If I insert into the middle the 4, 7, 5, that doesn't affect it. The 9 is still first. And then I can just keep going, you know, position that, and then now the tail is 8, 7, 9, and just and so on, right? Any questions so far? Give me a thumbs up if you're all caught up. Amber, Tate, Anthony, John, you're getting this right? Okay. If not, wake up and give me a thumbs up, and I'll never know. So anyway, I'm going to stop the share because that's the end of that particular lesson. Now, essentially what we've done is we've modified this list so that it has an insert at head and remove at head, and then an insert at and remove at. Now, here's the next thing I want to add. I'm going to add a method called insert at tail. All right, we've got an insert at head, and now I'm going to add an insert at tail. And this is going to allow me to add things to the end of the list whenever I want to. So I've got my insert at head, and now I'm going to do public void insert at tail and int value. And once again, this one will typically always work, so there's no reason to make it a Boolean. And because it will always work, I'm going to basically do the same code for insert at head. Let me make a copy and paste it here. Right, I'm going to make a new node. Oh, I should share this, right? All right, so I've got my insert at tail. I just wrote it right quick, and I just copied this. And now notice I say temp next equals head, right? And then head equals temp, and then if tail equals null tail. So this is the insert at head. So let me stop and point out what this is doing right quick. All right, remember that the insert at head creates a new node, right? Held in place with temp or something like that. We have this one point here, and then we have head point here. And if head started out, or if tail is null, we point at that. So that's all fine. Well, what I want to do now is insert at tail. So interestingly enough, well, I can create temp, right, just like I did before. Create a new node, right? But now what I want to do is set tail next equal to that, not head, right? So temp next is going to be null. That's no problem, right? Because it's going to be at the end of the list. Well, here's what I need to do. I need to make sure that tail is not null. If tail is null, then I'm inserting at the beginning of the list. So I need to set head and tail to point at this node. That's what happens if the list is empty. Now, if the list is not empty, then I simply want to set tail next equal to the new node, and then tail equal to the new node as well. So let's get this wrapped up here. So I'm going to start with if, let me get back here. If, and this is if the list is empty, so I can check head or tail. If head equals null, then so does tail, right? And if that's true, let me get this set up right, then head equals temp and tail equals temp. So I need to attach both of them because this list is empty. After I do that, I can return. Or I can just do else. Why don't I just do else? Slightly cleaner. Else, okay, I don't need to check anything else because now I know that tail is pointing at a node, and I know that it's pointing at the last node in the list. So I can set tail.next, right, equal to temp, and then I can set tail equal to temp too. I can get rid of this stray open parentheses that I have floating around, or open curly brackets. I don't need to type a return because it's a void method, but I do need to close the method. And so with the inserted tail, I need to worry about whether or not the list is empty, because if it is, then I have to update both the tail reference and the head reference simultaneously so that they're adding the one new node there. But if the list is not empty, then all I need to do is jack the new node into place. I can actually shorten this code significantly if I want to. Let me show you like a slightly faster way of writing this. I can basically set head and tail equal to a new node value and get rid of temp entirely, right? And then just say if the list is empty, right? Add the node, you know, with head and tail holding it. Okay. And then I can also set tail next equal to a new node. I need to do that here. And then I can set tail equal to tail next. All right. And these have the same effect. Because the tail node is always null, right? The tail next is always null. I can just add the new item directly to it. Right? Right, so the inserted tail is very easy. Okay. Any questions? Okay. Now, very briefly, I'm going to say why this is beneficial. Okay. And I'm going to also say why I did not do an insert at head. Okay. So let's address that question first. Why do I insert at tail but not remove at tail? I think I misspoke earlier. There's no reason to write a remove at tail. Okay. At least not with the singularly linked list where it's in one direction. And here's why. You just saw me insert at the tail because the null reference at the end allows me to attach a new node. It's just that easy. If I am looking at a node, I can set its next reference to a new node, and voila, I have added a node to that node. And then I just advance tail. So as long as I have a tail reference, I can just easily go beep, boop, beep, boop, and just add right onto the end of the list. Super easy. Okay. Removing at the tail of the list is really hard because I have to remove the element by using the node that's ahead of it. So I can only remove the last node if I'm at the second to the last node. And the only way to get to the second to the last node is to start at the first node and go all the way through the list. Well, if I've got 480,000 nodes, that's a lot of traversals just to pop the last thing off, right? So inserting at the tail is instant. It doesn't matter how many nodes there are on the list. If I have a tail reference, I know where the last node is and I can add there, bam. Also, inserting at the front of the list is super easy because I know where that node is and there's nothing in front of it. So I can make up a new one and look at the head and advance the head to that one, and I've got an item at the beginning of the list. Likewise, I can remove at the head of the list because I always know where the first node is. If I'm removing that node, the head reference is the only thing that's ahead of it. Because there's nothing ahead of it, I can just bypass it and get rid of it. So inserting and removing at the head, super easy. You just add an item using the head reference since there's nothing in front of it. Removing an item using the head reference, there's nothing ahead of it. So you're always ahead of the first node, if you will, because you have the head reference. The tail of the list is different though. It is super easy to insert at the tail because the tail reference allows you to add stuff on to the end because the end node is one ahead of where you're adding. But removing from the tail is a royal pain in the ass because you don't know that node in front of the tail, you can't get there easily. Now, why is this beneficial? Well, there are two data structures that are massively important in programming. One you already know about. It's called a stack. And a stack is a data structure where you add items at one end of the sequence and you remove items from the same end. Well, if you remove at and insert at the head of a linked list, you have a stack. You just have a stack. You can always add and remove from the head, and it will act exactly like a stack, which is beautiful. Now, a queue is a data structure where the items are taken out in the order that they are inserted. So if you insert 3 items, item 1, 2, and 3, you will remove them in that order. You'll remove item 1, then item 2, then item 3. Well, if you insert at the rear of a linked list, the tail of a linked list, and remove at the head, you can always insert items and then take them out in that order. So you have a queue as well. So with a linked list, if all you know how to do is insert and remove at the head, maintain a tail reference, and remove at the tail, then you not only have a linked list, it's not completely workable because you don't have the insert at or remove at, but you have a linked list, and you can use it as a stack when you want to, and you can use it as a queue when you want to. And this is just adding more skills to your skill set. Okay, so that's the lesson for today.